Hello, welcome to my channel. I am Ameya and we are discussing about time response specifications in control systems. Today we will discuss one problem to find various time response specifications from the given data. Okay, so the problem is for a system having g of s is equal to 15 upon s plus 1 into s plus 3 and h of s is equal to 1, we have to determine the characteristic equation, omega n and zeta, time at which first overshoot occurs, time period of oscillations, and number of cycles output will be performed before settling down. So here the given data is your g of s and h of s. Now we have to remember all the time response specifications are calculated depending upon closed loop transfer function. Here g of s and h of s is given, that means there is a unity feedback and open loop transfer function is given. So first we have to convert that g of s into a closed loop transfer function. Using a simple block diagram, you can convert this to form a closed loop transfer function, which can be given by g of s upon 1 plus h of s into g of s, okay, which can be equal to 15 upon s plus 1 s plus 3 upon 1 plus 15 upon s plus 1 and s plus 3. So if you try this to solve, final answer you will get is 15 upon s square plus 4s plus 18, and this gives you the first answer, that is your characteristic equation. Characteristic equation is denominator of your closed loop transfer function. So you can write your first answer as characteristic equation for this given transfer function is s square plus 4 of s plus 18. Okay, then we have to find zeta and omega n. To find that, what you can do is you can compare this to a standard form, that is s square plus 2 zeta omega n s plus omega n square. So you can easily compare omega n square with 18 and 2 zeta omega n to 4. From this you will get the value of omega n, which is 4.243 radians per second. Don't forget to write units. And after substituting that omega n in the second equation, this is the first equation, this is the second equation. After substituting omega in the second equation, you will get the value of zeta. So that zeta will be 0.4713. There is no unit for zeta, it's a ratio. So the characteristic equation is done. Natural frequency and damping ratio is also done. The next thing which we want to find is time at which the first overshoot occurs. Now the first overshoot occurs, that is your MP, and time associated with MP is TP. So basically you have to find this TP. You know the omega n value, you know the zeta value, you can easily find TP by substituting both of these values. The answer for TP will be 0.839 seconds. Don't forget to write units. So this third answer is also done. The fourth, what we want to find is the time period of oscillation. Now if you observe the previous video, we have understood that the system will start oscillating and it will get settled after some period of time. So after settling time, there is no oscillation. So here it is not given you have to find a settling time, but time period of oscillation is basically a time settling time. After settling, there will not be any oscillation. So we need to find Ts in this case. So it is not mentioned what Ts you need to find, criteria 2% or 5%, You can go with both if it is not asked. So you will get Ts is equal to, you know, the zeta and omega n, you can easily find the value of Ts. It will be 2.01 seconds for 2% criteria, and it will be 1.5 seconds for 5% criteria. Okay, so if it is not asked, you can always go with both the criteria and you can mention that answer in the final. Then you have number of cycles output will perform before settling down. Now this number of cycle is not directly a time response specification. We need to understand the number of cycles will be equal to omega d, which is your damped natural frequency that will basically absorb your cycles, and that will be for Ts. Cycles will perform till Ts. So that's why we are multiplying omega d into Ts. So value for omega d you can find by a simple formula. You have already substituted that in Tp, omega n under root 1 minus zeta square. That is your omega d. By substituting that value, you will get omega d, and then you can substitute, that is 3.75. So this will be 3.75, and you will substitute this with Ts. Now we have two values of Ts. So for 2% we will find number of cycles, and for 5% also we will find number of cycles. So you will get 7.5 cycles. You can round it off to 7 cycles. For 5% you will get 5.6 cycles. You can round it off to 6 cycles. So that is the answer for your number of cycles. So we basically found out the characteristic equation. Here we need to remember the denominator of your function, that is 1 plus h of s g of s, is basically your characteristic equation. And you have to, if it is asked for characteristic equation, you have to always compare denominator with the characteristic equation. Then we compared that characteristic equation with the standard form, that is s square plus 2 zeta omega n s plus omega n square. Then we found the omega n and zeta and rest of the things one after the other. So this is how you get the answers for time response specification problems. Thank you for joining.